Welcome to one more video on DSL3S. This time I will be showing the move operation, one of the key elements of the language. Before I start, just a quick note on this version of Eclipse I'm using. This is the latest release, Eclipse Luna. And what this means is that the plugins are now available from the update site for this version of Eclipse, and it's actually now recommended to use Eclipse Luna. It's also on the Wiki in the install instructions. Okay, in this demonstration I will be using a few spatial layers that we can see here in QGIS. There is a digital terrain model with altitudes from somewhere in the world, and then a vector layer with 3 points. And the goal for starters will be to make these points move downstream over the altitude. Before we start modeling, there are a few informations that we need to check here in our spatial data. Let's open the properties for the altimetry layer and take notice here of two important things. In first place, the number of cells we have in this layer, which will determine the space of simulation. So we have 150 cells by 100, and also the pixel size. We have 60 by 60 meters, so a square pixel. We'll use this information now during our modeling. So let's move on to Eclipse and start by creating a new project. This is a Java project. Can be called movement. Let's add the usual src gen folder to host the generated code, and then the libraries. I will have to add here the Mason, GeoMason and JTS jars. No, we want to stay with Papyrus. Okay, so I can delete the src folder, it's not needed. And before I start modeling, I can do another thing, which is to create a new folder called data, into which I will harbor the spatial data to be used in the simulation. So I can come here to the file system and copy the grid with the altimetry, and then this leads a shapefile that contains the water drops, and copy it here to the data folder. There they are. Okay, so we can start modeling. Let's create our Papyrus model. Let's call it movement. Again, it's UML, yes, and let's start with a class diagram, also called movement. And there it is. So first thing to do is to apply the profile. So we go here to the registered profiles. There is DSL3S. Select it. Okay. And we can start modeling. So let's start with the simulation class as usual, also called movement. And apply the simulation stereotype, which is here. Okay, so let's look into its properties. Again, we still have this issue with base class, so this is a bug, a very old bug with Papyrus. It's there registered, but as long as it's not solved, so you will be still seeing these rogue attributes. Just ignore them, please. Okay, so we can start by giving a name to our simulation. Movement demo. And here we have that information that we've seen before: space height, We have 100 cells, space width 150 cells, and yeah, that's all for the simulation element. So let's add now our digital terrain model. Let's call it just altitude. Let's apply the spatial stereotype. There it is. And let's look into the properties. So first place, I can give it the input layer, and since we have now the data in our workspace, I can refer directly to here to our data folder, and by checking here the name, so this is called alt 100 fill.agrid, and so we can leave it the default colors black to white, so that this will produce a grayscale, and that's it. We can leave everything else by default. So let's just assign altitude to the movement simulation. So now we'll create an element for the water drops. This can be called simply drop, and it's an animate, so we'll apply the stereotype. So again, we can give it here the spatial input layer, data folder, and the name is leads.shb. So what else do we need to do here? To give it some color so that it can be distinguishable from the DTM. So let's give it some red and without variation, since it's not really important, and we can leave everything else by default. So let's also assign this animate to our movement simulation. So now we can start relating the animate with other elements, but to do this, it's better if we create a new diagram, not to clutter this so much. So let's create a new class diagram for our water drop animate. So we can drag here the animate and the altitude, and now we can relate them with a movement operation. So let's call it flow, and apply the movement stereotype. Okay, so now let's look carefully here into the properties. There are two important properties here in the move operation. First of all, the scope. The scope basically determines an area around the animate. So it's a radius around inside which the animate will search for relevant elements for the movement. So we can start by giving this. So we have 60 by 60 meters in each pixel, so we can give it something like 90, which is not so far from the square root of 60. And then we have the weight. Now the weight will be applied on which element around the animate, and in this case we want the animate to flow downstream. We want it to prefer the places where the altitude is lower. So to do this, we can apply a negative weight. Now this weight can be used then in other with other elements, so with other operations, and we can give different weights to different elements, and this way make the animate prefer or prefer less certain elements. We'll see a bit more later on during this demo. Okay, so let's now assign this operation to the water drop element and relate it to the altitude. So let's save it, And we can now try to generate our simulation, see if everything went well. So come here to the UML file, right click, and ask MDD3S to generate the Java code. This later version of Eclipse shows this nice message here. So let's see the code, and we can run the GUI file as usual. Run as Java application. Okay, there it is. So I'll start by clicking pause, and this will simply load the spatial data and see what we get. Okay, so we have in grayscale the altitude as we expected, and in red the water drops. So let's see if this does anything. Okay, there we have our animats moving a bit slowly. This is a virtual machine, but as we can see they are slowly going downstream, so along the darker parts of our altitude. Now at some point we will see certain animats kind of staying in the same area, and this happens because there are some flat areas in this DTM. So when the animat is moving across an area where it doesn't find really different elements, so in this case, for instance, we see this animat here blocking here, it means that it is finding various elements but all with the same altitude, and in this case the animat simply chooses randomly one of these places to move into. So this other animat is still flowing downstream, so and it will, if we let the simulation run long enough, it will run down to the outlet. Okay, so let's stop and see a few other ways to use the move operation. Now I will add a new animat here so that we can show that we can see how animats can move relative to each other. So let's call this a follower. And the goal with this animat is that it will follow the water drops. Okay, so let's assign it to our simulation and apply on it the animat profile. Okay, so this animat will not be loaded from a spatial layer, so I will just inform here that I want 60 elements of this animat class to be created. So since there is no spatial layer, they will be cast randomly across the space of simulation. Also, I will inform that they are wanderers, so if they don't find anything interesting in their neighborhoods, they will be moving randomly. And now let's give it some color. This could be some green. And again, we don't need really to distinguish, so we can give the same color to minimum and maximum. And that's it for now. Okay, let's create also a diagram for this follower animat. Call it follower. And let's bring it. Okay. Now, I want follower to follow the water drop, but I cannot associate directly the follower to an animat. I have to associate it with an attribute. So in this case, we'll have to create a new attribute here in the water drop, which want too much really, but will serve as a kind of identity, and that's what I can call it, so that the follower animat can follow the water drop. So this is an attribute, and since this will be some sort of identity, I can just give it minimum and maximum values and of 1 and an initial value of 1. So as I associate this identity attribute to drop, every drop element will have an attribute called identity, always with a value of 1. So now I can associate this by bringing here the attribute identity, and now I can associate. So let's call this follow. It will be again another move operation. And okay, so what I will give it here is a positive weight, and since there is no other element, so 1 is enough. And since the identity here is also a positive value, so it's also 1, so this will be seen by the follower animat as an interesting place to be with, as an attractive place to be with. And then the scope, I will give it slightly larger scope, so that if the follower identifies a water drop in its scope, it won't let the water drop go away. So now I have to assign this operation to the follower animat and then relate it to identity. Okay, so let's see now what this does. Again, generate the Java code. I have a few more files there. Let's run our model. Okay, so let's load the data again. And there we have it. Again, we have in the grayscaled DTM, then in red the water drops, and in green the randomly cast followers. So as we have set the followers to wander, they will move randomly, and then when they get into the distance that we set in the follow class to a water drop element, they will follow, and if we wait long enough we'll see this happening at some point. Okay, so we have here already, no, not yet, it just was close enough. Okay, so we have already one follower following here water drop, and as we let the simulation run, we'll see more and more followers going after the water drops. So this is an example of how the move operation can relate to different animats. Okay, so let's stop this and see one more way of using the movement operation. So as we have seen now, this mostly relations of attraction or of following or dragging, and now we can try something in the opposite way. So if we go back here to QGIS, there is an extra spatial layer called barriers, with two vectors that are cast here over the two of the streams that the animats will follow. And so the goal now would be to tell the animats that they cannot pass over these barriers. So let's go back to our model again. Let's in first place copy the barriers shapefile, which is also here in the file system. Let them go to the data folder, and now create a new spatial variable here in our model, and barrier, I think it's the appropriate name. Let's apply again the spatial stereotype, and for the input layer let's give it data, and the name was barriers.shp. Okay, colors, so this can be blue, so let's give it a lighter blue, these guys. Okay, and we can leave everything else by default. So let's assign this to our simulation. So as you can see, our model is getting already a bit cluttered. That's why it's useful to use views or diagrams to compose our model. Okay, and then let's go to the water drop and relate water drop with the barriers spatial. So let's drag it here, and again the same method. Create a new movement operation, call it halt, and apply the move stereotype, and there it is. So we'll use the same scope, 90, and then weight we can use a very large value, a very large negative value. Let's put 1000, and so this will simply make all the areas where there is a barrier over which really unattractive, and so the animat won't move into it. So we can leave everything else by default. Let's associate this to our drop animat. Let's make this a bit more visible, and now then to the barrier. Now one thing is that we have given here a negative, so we have here a negative weight, and since we want it to work as a deterrent, so to say, I have to make sure here that the barrier has a positive value, so we have positive with negative. Okay, so let's save and see if this is actually doing what we wish it to do. Generate a simulation. And we have 2 more files. Let's run it. Okay, so let's load the data. Okay, there we have now in blue the barriers, and then let's see the result. So there the drops going downstream slowly, eventually dragging a follower along if they get close enough. So this is somewhat slow, It's running on a virtual machine, so this is in a different system. This will be considerably faster. So we have here to the east this animat slowly going downstream. Already dragging along, and then it stops there. So as you can see, the follower keeps following, but the water drop doesn't go further. So as we've seen before, this water drop would come into this this valley here, and now it's there and it stops. So again, as this is a kind of a somewhat flat area, so the water drop won't stand still, so it will still move around and select randomly among these even altitude values, but it won't go further beyond the barrier. Okay, so that's it for this demo. Thank you for watching, and keep an eye on the videos page in the wiki, because there is certainly more to come. Thank you, and see you another time.